Welcome back. In this last lecture for Chapter 9, which is a portion of Module 3, we're going to discuss divergence and curl. So we're going to do this less from a mathematical point of view, so I may be skipping over some of the abstract mathematical proofs because I'm more interested in you learning the divergence, just the actual physical operation. But we will try to discuss so that you get a little physical insight. So divergence is an operation that is done on a vector field or on a vector. So we have some vector in Cartesian coordinates x, y, and z, where v1, v2, and v3 are the components of v. So when we take the divergence of v, then we get the partial of v1 with respect to x, the partial of v2 with respect to y, the partial of v3 with respect to z, and that is a scalar. So here is an example where we have this vector field and it's a multivariable function. So in order to take the divergence of this first component, we would take the partial with respect to x, which would leave us with 3z. Here we would take partial with respect to y, which would leave us with 2x. And here we would take partial with respect to z, which would leave us with minus 2yz. So that's how the divergence operation is conducted. The divergence operation gives you an idea of how directed is your field. So another common notation for divergence, once again, this G should be a dot. It's del dot V, so it's the dot product between partial with respect to X, partial with respect to Y, partial with respect to Z, dotted with V1, V2, and V3. And so the product means the dot product, but actually when you do the dot product, because this contains the differential operator, you're going to have to take partial derivatives. So that comes about as part of the dot product. Here's the result of that. Fortunately, no confusing little g's here, which should be dots. So anyway, this basically gives you a scalar. It's sometimes referred to as a scalar divergence. So del dot v, the del dot is an operation that can only be done on a vector quantity, whereas the gradient del of f is done only on a scalar quantity. The divergence depends only on the point in space because it is a scalar. So if we had a different coordinate system, if we had a spherical coordinate system or a cylindrical coordinate system, the value of the divergence at a given point would be the same. So it's invariant across coordinate systems. And then if we take the divergence of the gradient, so if we have a scalar quantity f, and if we take the gradient of f, we obviously will get a vector quantity. And then if we take the divergence of that vector quantity, we'll get a scalar quantity back. This is referred to as the Laplacian, the divergence of the gradient. It's referred to as the Laplacian, and it is sometimes written del squared f. And yes, I know this is not a delta. It's an inverted delta, but it is still sometimes referred to as del squared f. And then we will kind of skip over some of this stuff on compressible fluids because you guys are not mechanical engineers, and let's go straight to the curl. So the curl of a vector field gives you an idea of how much. So while the divergence gives you an idea of sort of how much spread there is in the field, the curl gives you an idea of any rotation in the field. So if there's no rotation, then you have no or very little curl. In field theory, which is once again the best example I can think of to illustrate some of this, some of these concepts from an electrical engineering point of view, you may remember that the current wraps around a magnetic flux, or a magnetic field will wrap around the current. So the relationships for current and magnetic field in magnetostatics are curl relationships because one rotates around the other. And so that's whereas in the electric field and electric potential and voltages, the relationships are divergence relationships because there's not rotation. There's a single charge that is creating a field, and then everything else is linear superposition. So the curl can most easily be written as del cross V, and the easiest way to calculate it is to use a determinant where the first row is I hat, j hat, and k hat. The second row are the partial derivatives with respect to x, y, and z um, respectively, and then v1, v2, and v3, the components or the coefficients of the three dimensions. Um, this is once again for a right-handed coordinate system. Please ignore this second sentence because we're not dealing with left-handed coordinate systems at all. So this basically is your curl equation. So gradient fields are irrotational. In other words, if a continuously differential vector function is the gradient of a scalar function, then its curl is 0. So the curl of the gradient is 0. And furthermore, the divergence of the curl is 0. So what this means is this means that once you have calculated a gradient, then you have a directional vector and there's no rotation. So the curl would be 0. Once you have calculated the rotation, you're in a direction that is orthogonal to the vector flow. So the divergence of that orthogonal direction will also be 0. So it's a complicated thing to visualize for electrical engineers because it's kind of a spatial concept. So, I'm fine if you just remember these two things. These two things do turn out to be fairly important. Once again, I'll use field theory as an example. In electromagnetic fields, when we get ready to solve for things like the wave equation and the continuity equation, knowing these vector relationships are important because they allow us to perform certain operations on the field vectors, which then allow certain things to go away to 0 and for us to apply certain theorems to the problem. Okay, once again, the curl is invariant. It is a vector, but it does have a length and a direction that are independent of the choice of Cartesian coordinate systems in space. So you will get the same um, Cartesian vector coordinate for the curl. If you're doing this in spherical or cylindrical coordinates, same thing will apply. You won't get the same number because the spherical and cylindrical coordinate systems have different unit vector approaches. But if you were to then calculate a magnitude and direction and do a transformation from that spherical coordinate system to a Cartesian coordinate system, you would get exactly the same thing for the curl. So it doesn't change, it might look a little different. So just a summary of vector calculus then, the gradient, the divergence, and the curl. So you have some vector of form a1, a2, a3 in Cartesian coordinates. It's in real number space. We've looked at vector addition. We've looked at component-wise scalar multiplication. Once again, we're not doing anything at this point with complex numbers. We're also doing, addition. We talked about the inner product or the dot product. We talked about the outer product or the cross product. We talked about the length of a vector. We talked about this right-hand rule, this right-handed triple. We talked about the cross product. We said the cross product is not commutative, so A cross B does not equal B cross A. We talked about the triple product. We then extended differential calculus to vector functions and defined the derivative of a vector, in this case with respect to time. We looked at some of the different differential rules in calculus that apply to vectors as well. We did not talk about curves in space. We did talk somewhat about partial derivatives. We talked about the gradient. We mostly skipped over a directional derivative, but this is the summary formula. So if you have a direction vector A Then the derivative of f in the direction of vector A is given by 1 over the magnitude of A dotted with gradient f. We defined divergence and we defined curl. And once again, please ignore the comments about left-handed coordinate systems. Only mathematicians care about that. So this pretty much summarizes the vector calculus hitting the high points in chapter 9. As I said in the introductory video, really most of this should be review. If there's some segment of this that for whatever reason you missed in your undergraduate education, and I understand that we have people from all over the world coming from all different mathematical backgrounds. So if you feel you need more than what we've had in just this brief kind of brush over of vector calculus, then I would highly encourage you to go to the Khan Academy site as well as to the textbook and read in more detail than what we've covered here in these short video lectures.